This lecture looks at one-dimensional two-source interference. So we have waves, we have two sources, each giving off a wave that travels along the x-axis. And then we'll look at how the waves overlap and how they interfere. Do they interfere and give something bigger, or do they interfere and give something smaller, totally cancel each other out? How do we figure all this out? So if we start off with a little animation, we assume we have two sources that are situated at a distance delta x apart from each other. So one source is at some position and another source is a certain distance away. They're both on the x-axis. They give off waves with the same wavelength and same frequency. So we'll assume it's the same type of wave, sound wave, wave on a string, whatever it might be. And we'll assume that the wave that's to the right, or the source that's to the right, does not block the wave from the source that's to the left. So somehow we can make this work. Both waves are traveling to the right. So both sources create waves that are traveling to the right. So the resultant wave is a combination of two waves that are traveling to the right. And we'll assume that the wavelength of each of the waves is 2 meters. And initially, at least, we'll have a delta x, the distance between the sources, equal to 1 meter. So that's what this animation starts off looking like. So right now, I've got this set up so that this little slider can adjust delta x, the distance between the sources, and it's set at 1. And then you've got the phase constants for each of the waves, and we'll look at this mathematically in a second. But if we think about each wave as being a sinusoidal wave, there's always this phase constant in the argument of the sine function that you can set to be some value depending on what's going on at t equals 0 at the source. So we're just starting off with both phase constants equal to 0. So they're exactly the same. We would say that these sources are in phase with each other. And so if they're separated by 1 meter, then this graph here is this red graph is the wave that has been emitted by the source at a position of -1 meters. The blue graph is the wave emitted by the source that's at 0. So there's a source here at 0, there's a source at -1, and they've emitted waves for a while, and we've taken a snapshot of those two waves. And you can see that at this moment, when we've taken this snapshot, at this moment, this source here has just given off a minimum. It has traveled to the right a little bit. And also this source here at 0 has just given off a minimum. So that's telling you that these two sources are doing the exact same thing at the same time. At this instant, when this picture is taken, this source here at 0 and this source here at -1 are both in their equilibrium position. And as time goes on, if we step through time a little bit, we'll see that at a slightly later time, each of these sources will then give off a maximum. So let's just step through the time. So you can see right about now, the sources are both giving off a maximum. And so the source at -1 is giving off a maximum, the source at 0 is giving off a maximum. So we say that these two sources are in phase with each other. And that's reflected by the fact that they have the same phase constants. The difference in these phase constants is 0. They're identical. Now we'd get the same thing if I changed the two phase constants and made one of them 3 pi over 8, and I'll make the other one 3 pi over 8. Again, it looks the same. When one source is giving off some kind of a wave, in this case it's not quite a maximum, but the other source is doing the exact same thing. It has just given off the same wave. If I advance time a little bit, you can see when they're giving off maximums. So right now, this source here is giving off a maximum, this source here is giving off a maximum. So what's important is not so much what the phase constant is for each individual source, but the fact that they're identical. The two phase constants are the same, 3 pi over 8 and 3 pi over 8, same phase constants. So they're in phase with each other. So we'll be looking, that's going to be a critical thing to determine what's happening with the waves that these sources create. How do they overlap? One big factor is the difference in these phase constants. And the other big factor is the distance between the sources. So right now that distance is set to 1 meter. That's a half a wavelength. And you can see that once these waves overlap, this source at -1 has a wave that travels along, and then the source at -2 has a wave that travels along. Once we get into a region of space over here where the two waves are existing in the same place, we can see that a maximum of one wave is always overlapping with a minimum of another wave. So this green line that you can barely see here is the resultant wave, the sum of these two sine functions. and it's perfectly flat. It's nowhere on the x-axis is it anything but flat. That means that everywhere on the x-axis, the total wave is 0. We have complete destructive interference. And as time goes on, it just remains complete destructive interference. So if you're sitting here at point number 3, if all you could do is measure the wave coming from the source at -1, you'd see a maximum in displacement. If all you could do is measure the wave coming from the source at 0, the blue wave, you'd see a minimum of displacement. But really what we do is we always measure the total. That's all we can really do, is always measure the total displacement of the medium. And that would be the green curve, and that would be 0. So if we're sitting here at point 3, we'd be measuring 0 displacement of the medium. And let's play this and see. If we let time go by, both the red and the blue curve move to the right, and they're always staying in the same phase relationship relative to each other. There's always maximum on top of maximum, or maximum on top of minimum. And so the green graph is always 0 for every place on the x-axis. And that's because we have a particular difference in phase constants of 0 in this case, and a particular distance between the waves of a half a wavelength. That causes the two waves to completely cancel each other out. The resultant wave, the thing that you would actually hear if these were sound waves, this green wave, is totally flat. There's nothing there. So we have complete cancellation of the sound waves. So now let's pause this and then bring it back to the beginning. Now again we have the phase constants the same, but now we change the distance. If we gradually change the distance, you can see what happens to the sources. If I change the distance to say one wavelength apart, one full wavelength apart, when one wavelength, remember, is 2 meters. So bring this to 2 meters. So my sources are 2 meters apart. One source is at -2, the other source is at 0. And you can see that the red graph perfectly overlaps with the blue graph. And so the result is that the green graph, which is the total, is big, is very large. So we have very strong constructive interference because these waves are overlapping maximum on top of maximum. So they still have the same phase constants. We would say that the sources are still in phase with each other. When, in this particular instant in time that I'm sort of taking this snapshot, the source at -2 has just given off a minimum. The source at 0 has also just given off a minimum. And so they're in phase with each other, but they're separated by a full wavelength, so that as this wave comes along and it finally encounters the wave by the second source at 0, it overlaps perfectly with that second wave. And so the two waves overlap perfectly, maximum on top of maximum. We have constructive interference. So we can adjust all these different things. If we have, let's bring the distance back to 0. If we bring the sources to the same location, again we have them overlapping completely. We have one source at 0 and another source at 0. They're both at 0. The blue and the red graph overlap perfectly. You can't really see the red graph. And the green graph is the sum of the two graphs. And so it looks perfectly maximum in a sense. So you have maximum constructive interference. So whether you get constructive interference or not depends on two factors. It depends on the difference in phase constants of the sources, which tells you what one source is doing relative to another source. Are they doing the same thing at the same time? If that's the case, then the phase constants are the same. Or are they doing sort of the opposite thing? And we'll look at that in a second. Is one giving off a maximum while the other is giving off a minimum? That will change things. So that's a big factor in whether you get what kind of interference you get. And also the distance between the sources is another just as important factor. So before we go to the mathematics of this, let's just change this. Let's make this phase constant 0, and let's make this phase constant pi. So one phase constant is pi, one phase constant is 0. The sources are at the same exact location, at 0. So both sources are right here. At this particular moment in time, the red source has just given off a maximum, while the blue source has just given off a minimum. And so as these waves travel, they're always going to be lined up in such a way that a maximum of one is on top of a minimum of the other, and vice versa. And for any moment in time and any position on the x-axis, then you're going to have complete cancellation of those waves. If I play this now, the waves move to the right, and the green graph is always flat. It's perfectly flat. So there's total destructive interference for every point on the x-axis as time goes on. If I go to some intermediate value, if I don't have a phase constant of pi and another one of 0, so the phase difference between the sources is pi here. If I have something else, just select the value 3 pi over 4 and 0. That makes them not quite line up perfectly. You don't have maximum on top of minimum, nor do you have maximum on top of maximum. It's somewhere in between. And so when you add these two curves together, the red and the blue, you get something that's sort of somewhere in between. In this case, you get a green graph that looks like this. And so the maximum of the green graph is actually a little bit less than the maximum of either the red or the blue. And so this is some degree of destructive interference. The total resultant wave is a little bit smaller than one of the individual waves. So you get some cancellation, but not complete cancellation from the two waves. And again, as you play this, as you let time go by, if you're sitting at a point, let's say 3 meters, you're going to be measuring that green graph. And you're going to see the medium going up and down or vibrating in some way, but not at the biggest vibration it can have. It's going to be vibrating less than if you just had a single source. There's some cancellation here because of the destructive interference, because of the phase difference between the two sources, the difference in the way that they're vibrating relative to each other. And so you can adjust all these things, and I encourage you to play with this animation. This will be available as a Mathematica computable document format that you can play with the free Wolfram CDF player that you can get. So let's quickly look at the mathematics of adding these kinds of waves together. So if we look at the sort of standard equation for sinusoidal waves, the displacement of the medium is an amplitude times sine of kx minus omega t plus a phase constant. K again is 2 pi over the wavelength, and omega is 2 pi times the frequency. And this phase constant is somewhat arbitrary, but what it determines is if you plugged in time equals 0 and x equals 0, x equals 0 is typically the position of the source, t equals 0 is time equals 0. What the phase constant would tell you is what is the displacement of the medium at that position and at that time. That's how you determine what that phase constant is. So we have two sources. So we're going to have two equations, one for each source, the displacement of the medium due to source 1 and the displacement of the medium due to source 2. We'll assume that both of them are exactly the same in terms of their amplitudes. The individual amplitude is a, little a, we'll call it. So each source vibrates the medium in exactly the same way with the same amplitude, same wavelength. Wavelength is embedded inside of k here, and same frequency, omega. And they may have different phase constants, Phy222 or Phy222. So what we do then is, physically when these two waves are being emitted and combined on the x-axis, that's described mathematically by just adding these two displacement functions together. So when you add these two sine functions together, there's a trig identity you can use, and you can ultimately find that the sum of this sine plus this sine is equal to this stuff here. And it looks a little crazy and ugly looking, but it's not terrible. You've got a sine function piece, and then you've got a cosine piece in here too. So what the sine function piece tells you is it's a function that has some k times the distance times x minus omega times t plus some angle. That sine function is just part of a traveling wave. It's just that sinusoidal traveling wave, kx minus omega t. This tells you that you've got some traveling wave. You're adding two traveling waves together that are traveling to the right, and you get another traveling wave, travels to the right. Kx minus omega t travels to the right. However, the amplitude of the sine function is a bit complicated. The amplitude looks like this thing in square brackets here. If I can highlight it carefully, not highlighting very well, but anyway, this 2 little a times cosine of all this stuff is the amplitude of this sinusoidal traveling wave given by the sine function. So what do we have inside the cosine? Well, we have the difference in positions of the sources. That is delta x. That's ultimately the distance between the sources. And we also have that phase constant difference. We call that delta phi 0. So let's write that down here. Let's take this stuff, leave the 1/2 for a second, take k times delta x, and then plus delta phi 02 minus plus phi 02 minus phi 01. We'll call that difference in phase constants, we'll call it delta phi 0. So that's this guy here. k is 2 pi over lambda. So that's this right here, 2 pi, and the lambda is down here. And then x2 minus x1 is delta x, right there. So all this stuff in the curly brackets here, we refer to as delta phi. Delta phi is what we call the phase difference between the waves created by the two sources. Delta x is the distance between the two sources, and delta phi 0 is the phase constant difference between the two sources. So again, this phase constant difference, each individual phase constant tells you what each source is doing at time equals 0 and at x equals 0. The difference in these phase constants basically tells you what the two sources are doing relative to each other. If this phase constant difference is 0, that means they're doing exactly the same thing at the same time. If that phase constant difference is pi, that means they're doing opposite things at the same time. We say that they're out of phase with each other. And so this delta phi is a critically important thing. It's inside of this cosine function, and that cosine function is part of the amplitude of this traveling wave that you ultimately measure. And then we can write the amplitude as it's 2a cosine of all this stuff, so that's 2a cosine of 1/2 this delta phi thing. So the way we use this is we say, okay, let's pick a point on the x-axis. From that point, we can measure the values of x1 and x2, and we subtract them. And that's basically just the distance between the sources. So we put that in here. And then we say, what about the phase constants of the two sources? So how are they vibrating relative to each other? If they are vibrating in phase with each other, we say that delta phi 0 is 0. If they're completely out of phase with each other, which means they're doing the opposite thing at the same time, then this delta phi 0 is pi. Opposite of things, we think about things in terms of cycles. When one thing is vibrating and maybe it's giving off a maximum, the other thing, if it's out of phase with that first thing, it would be giving off a minimum. So a minimum and a maximum are like half a cycle apart, 180 degrees or pi radians. So delta phi 0, the difference in the phase constants would be pi radians if the two sources are completely out of phase, doing opposite things relative to each other. So you determine those two things, the distance between the sources, and the difference in the phase constants. That would give you ultimately the phase difference between the waves themselves that are being added together. And then the amplitude of the resultant wave is simply 2a cosine of that phase difference divided by 2. So what would make this big? What would make this small? If I had, let's say if I had delta phi 0, or delta phi equal to 2 pi. If delta phi turned out to be equal to 2 pi, once I put in delta phi 0 and delta x, then I would have 2 pi divided by 2. That would be pi. Cosine of pi is minus 1. The amplitude would be minus 2a. And we think in terms of absolute values. A minus 2a multiplying the sine function means that we're vibrating with large amplitude from minus 2a to plus 2a, because the sine function goes from minus 1 to plus 1. So a delta phi of 2 pi is going to give us large amplitude. The same thing would be true for 4 pi, a delta phi of 4 pi. If I have 4 pi divided by 2, that would be 2 pi. Cosine of 2 pi is plus 1. My amplitude would be 2a again. So in summary, anytime that delta phi is an even multiple of pi, you're going to divide by 2 in here, and you're going to get cosine of that thing that's a multiple of pi. And cosine of any multiple of pi is plus 1 or minus 1. It's going to give you the biggest amplitude you can get, positive or negative. However, if this delta phi is, let's say this delta phi is just pi. Let's say it just turns out to be pi. Not an even multiple of pi, but pi. Then when I put that in here, I'll have a pi divided by 2. Cosine of pi divided by 2 is 0. Cosine of 90 degrees is 0. That means my amplitude is 0. That means I have total destructive interference. The two waves cancel each other out completely. So how do you get a delta phi of pi? How does this become pi? Either, there's two ways, there's actually many, infinite number of ways, but one possibility is if the two sources are at the same exact location, that delta x would be 0, and then if this phase difference was pi, that would make the wave's phase difference be pi. The phase constant difference being pi means that the two sources are doing the exact opposite thing at the same time. And we saw that in the previous animation. If the two sources are at the same location and they are doing the opposite things at the same time, one's giving off a maximum while the other's giving off a minimum, then the two waves are going to add up destructively, completely destructively with each other. So that's one way that you can get a delta phi of equal to pi. Another way is if the sources are exactly in phase with each other, if the delta phi 0 is 0, they're doing exactly the same thing at the same time, then if delta x is equal to a half a wavelength, if delta x is equal to 1/2 lambda, then I have 1/2 lambda divided by lambda, that's 1/2, times 2 is 1 single pi, 1 pi. So I could get a phase difference between the waves of pi if I have a phase constant difference of 0. The two sources are exactly in phase with each other, but they're separated by a half a wavelength in distance. Then again, I would have the two waves overlapping, maximum on top of minimum, and I would have total destructive interference. My total amplitude of my resultant traveling wave is going to be 0. So that's some examples that you can think about, but there's all kinds of other possibilities. You can have all kinds of possible values for delta phi 0, all kinds of possible values for delta x. The bottom line is if this delta phi comes out to be an odd multiple of pi, then you're going to divide that thing by 2, and you're going to get an angle in here in the cosine function that makes cosine of that angle equal to 0. You're going to have total destructive interference. And then if you have some value of delta x and delta phi 0 that makes this delta phi equal to an even integer times pi, then you're going to divide by 2, and you're going to have some integer times pi, maybe 1 pi, 2 pi, 3 pi, 4 pi, whatever it might be. Cosine of that is either going to be +1 or -1, and that's going to make the amplitude as big as it can get. It'll make your traveling wave your ultimate resultant traveling wave as big as it can get. You'll have complete constructive interference. So we can go through and look at a bunch of examples of this, but I encourage you to play with these numbers, play with these animations, and remember these two equations. They're key to to understanding all this. So again, we can have our wavelength is again 2 meters. We can have a separation of 1 meter, that's a half a wavelength. And the two waves are in phase with each other. They're the same phase constants, so the phase constant difference is 0. And you can see that because they're separated by a half a wavelength, that when one wave overlaps with the other one, they overlap maximum on top of minimum, and they totally cancel each other out. And that's true not just for one moment in time, but as time goes on, at a given point in space, that green graph is always flat, and it's always 0. You've got cancellation everywhere and for all the time. And then if you change things, if you change the distance slightly, then you shift the waves a little bit relative to each other, and now you don't have complete cancellation anymore. You get something that's kind of in between. The green graph is a little bit bigger now. The green graph is still not as big as one of the individual waves, so this is more destructive than it is constructive, but it's not 0. So sitting at 0.3 here, we'd be measuring this green line going up and down, this displacement of the medium vibrating back and forth with an amplitude given by the green line, the green graph. If we continue to change the distance a little bit, we can get those two waves, the red and the green, red and blue guy, to overlap better, and we get more constructive interference than we have destructive. But it's not complete constructive, somewhere in between. So definitely, download the CDF file for this. You can play with these sliders and see how changing phase constants and changing distance between the sources affects the nature of the interference, whether it's constructive or destructive or somewhere in between. So have a good rest of your night, and we'll talk to you soon.